Are you the kind of person who wants the truth before the headlines get edited? Subscribe right now, because what NASA insiders saw this week didn't make the press release. Something strange just showed up in the newest images of 3i, Atlas. And the people who work closest to the data aren't reacting the way you'd expect. In this video, you're going to see what changed, why astronomers are uneasy, and what the public version of this story leaves out. For months, 3i Atlas was just a dot on tracking charts. The third confirmed visitor from outside our solar system, following in the footsteps of Oumuamua in 2017 and 2i Borisov in 2019. At first, everything about it looked boring in a good way. Fast, hyperbolic path, coming in hot from deep space. Another chance to study material from another star system, the kind of thing that makes scientists excited, not nervous. Then the new images came in. People inside the observation teams at NASA Jet Propulsion Laboratory started sharing quiet notes. Not to the public, not on social media. In internal channels used by analysts who work with Hubble spectrograph records and James Webb Space Telescope data, the tone shifted. Less celebration. More double check this. More, does anyone else see that? More silence. The object was first flagged as a faint speck moving against background stars. That's how almost every interstellar visitor starts. You blink and the dot has shifted. You run the numbers. The numbers say it's not bound to the Sunday. That's how you know it came from somewhere else. That's how Oumuamua was found. That's how Borisov was confirmed. And that's how 3i Atlas entered the charts. But 3i Atlas didn't behave like the others for long. When the Hubble Space Telescope locked onto it for follow-up, the dust tail looked wrong. Not impossible, but wrong in a way that makes scientists uncomfortable. In most comets, solar radiation pushes dust away from the sun, so the dust tail points away. That's basic physics taught in school. With 3i Atlas, early images showed a dust structure that appeared angled toward the Sunday. Not cleanly, not like a perfect arrow, but enough to raise eyebrows at the European Southern Observatory and among teams pulling data from Keck Observatory in Hawaii. At the same time, spectroscopic scans showed something missing. Normal comets light up with gas when they heat up. You see water vapor, carbon monoxide, carbon dioxide. Those gas jets are what create the classic glowing coma. With 3i Atlas, early scans showed dust, but very weak gas signals. That's unusual, not impossible. But unusual enough that Harvard-Smithsonian Center for Astrophysics researchers flagged it for deeper follow-up. Then the speed numbers landed. 3i Atlas is tearing through the inner solar system at around 130,000 miles per hour. That alone isn't shocking for an interstellar object. What caught attention was how steady the motion looked when analysts overlaid light curve data. Light curves tell you how brightness changes as an object rotates. The pattern from 3i Atlas suggested a stable rotation period, roughly in the range of hours, not minutes. That stability hints at a solid structure. Again, not proof of anything strange. Just another check mark on the "this one is different" list. Now here's where the path starts to feel uncomfortable. When NASA JPL ran long-range trajectory simulations, 3i Atlas didn't just pass through empty space. Its inbound path brings it relatively close to Mars, then later near Venus, and later still toward Jupiter's neighborhood. In cosmic terms, close can mean tens of millions of kilometers. So nobody is saying it's going to hit anything. But lining up near 3 major planets in one pass is rare. The math says it's unlikely, not impossible. And when unlikely things pile up, scientists stop shrugging. People sometimes forget this, but NASA plans its own spacecraft paths the same way. The Voyager missions use gravity assists from planets to sling around the solar system. Stanford researchers studying Ronald Bracewell's old probe concepts even modeled how a probe could pass near multiple worlds with minimal fuel. So when an interstellar object threads a path that looks like something an engineer would design, even by accident, it gets noticed. Then there's the timing. 3i. Atlas reaches perihelion, its closest point to the sun, during a window when the sun's glare blocks direct observation from Earth. This happens to comets all the time. Solar conjunction is a known blind spot, but the coincidence means the moment when 3I, Atlas, is brightest and most active is the moment when Earth-based telescopes can't see it well. Hubble can't point that close to the Sunday. James Webb has strict sun avoidance angles. Even ESO's ground observatories lose the target in glare. So the most important moment happens behind a bright curtain. Astronomers hate blind spots. Inside NASA JPL, analysts leaned harder on indirect data. How does the brightness change before and after conjunction? Does the coma grow? Does it fragment like Borisov did? Does the dust pattern shift? The Vera Rubin Observatory, even during early operations, added pre-discovery images that showed 3I, Atlas, before it was officially announced. Those frames confirmed the odd dust behavior was present early, not just a one-off glitch. And that's where the leak story comes from. Not secret files, not some movie-style folder stamped top secret, just unreleased frames that hadn't been cleaned up for public viewing yet. Raw images look messy, cosmic rays, sensor noise. But in those raw frames, some analysts thought they saw structure in the dust tail that didn't fit simple models. When those impressions got passed around privately, the mood changed. Not panic, more like that quiet moment in a lab when people stop joking. Now let's be clear and strike safe here. Nobody at NASA has confirmed anything wild. No one is saying, this is a craft or this is a threat. The public statements remain calm. 3I. Atlas is described as a likely natural interstellar comet, and that's still the most reasonable explanation. But scientists are human. When something looks odd, they stare at it longer. They run more models. They argue late into the night. And that's what's happening here. The James Webb Space Telescope is scheduled to observe 3I, Atlas, in infrared, to look for heat signatures and chemical fingerprints. If there are exotic ices, Webb can spot them. The Hubble spectrograph continues to track dust behavior. ESO teams compare polarization data to estimate surface texture. Keck Observatory helps with high-resolution tracking. Arecibo legacy data even helps calibrate how radar echoes behave from unusual objects, even though Arecibo itself is gone. This is the full weight of modern astronomy leaning in. There's also a quiet defense angle. The US Space Command tracks objects for space situational awareness. Planetary defense groups model fast movers as practice cases. Nobody is sounding alarms publicly, but analysts use real events like this to test detection pipelines. Can we spot something fast? Can we update orbits quickly? Can we share data between agencies? If a real threat ever showed up, these drills matter. So 3I, Atlas becomes both a science target and a systems test. What makes people uneasy isn't one anomaly. It's the stack. A dust tail that looks wrong, weak gas signatures early on, a statistically odd planetary path, a solar glare blackout at peak activity, and the sheer speed of the object. None of these alone mean anything strange. Together, they keep scientists awake. There's also history whispering in the background. Oumuamua showed unexplained acceleration that took years to model as likely outgassing of hydrogen or nitrogen. Borisov fragmented in ways that taught us interstellar comets can be fragile. Each visitor forces astronomers to update their mental model of what normal looks like outside our system. 3I, Atlas, might just be the next update. Or it might be the one that breaks a few assumptions we didn't even know we were making. What happens next is the real story. When 3I, Atlas, reemerges from behind the sun, astronomers will compare before and after data. Did it shed more dust? Did new gases appear? Did the rotation rate change? Did the coma suddenly flare? NASA JPL will refine the orbit. Harvard-Smithsonian teams will update composition models. Webb will add infrared fingerprints. If it fragments, we learn about its inside. If it doesn't, we learn about its strength. Either way, this is a once-in-a-lifetime lab experiment flying through our neighborhood. So here's the uncomfortable truth. The leak didn't reveal a secret, it revealed uncertainty. And scientists don't like uncertainty when the data pile up in strange ways. 3I. Atlas is probably a weird but natural comet from another star system, but probably is not the same as understood. And right now, this visitor is teaching us how little we really know about what drifts between the stars. The problem scientists now face is simple to say, but brutal to deal with. We only get one pass at this object. There's no second chance. 3I, Atlas is moving too fast for any spacecraft we could launch today to catch it. Even if NASA, ESA, or a private company hit the launch button right now, the physics doesn't work in our favor. By the time a probe got up to speed, this visitor would already be gone, slipping back into interstellar space for millions of years. So every answer has to come from a distance. That's why the blind spot near the sun is such a headache. The moment when 3I, Atlas, is heated the most, when hidden gases might erupt, when cracks could open and dust could burst out, is the exact moment when Earth's best eyes are forced to look away. It's like trying to understand how a person reacts under pressure, but the camera cuts out right when things get intense. Teams at NASA Jet Propulsion Laboratory ran models to predict what should times happen during perihelion. If 3I, Atlas, behaves like a normal comet, its activity should spike. Gas jets should turn on. The coma should thicken. Dust should stream away in clean arcs shaped by solar radiation. When it reappears from behind the sun, we should see the aftermath of that heating event written all over it. But what if that doesn't happen? That's the uncomfortable question no one likes to say out loud. Not because it means something sci-fi, but because it means our models are missing something basic. It would mean that interstellar objects don't just come in different sizes and compositions, but sometimes behave in ways we haven't seen before. And if we can't predict their behavior, we can't easily predict how future interstellar visitors might interact with our system. Now zoom out for a second. This isn't just about one object. This is about what 3I, Atlas, represents. Every interstellar visitor is a free sample from another star system. We didn't have to launch a probe across light years. The galaxy sent us one. That's why places like the Harvard-Smithsonian Center for Astrophysics and teams working with James Webb are treating this like a gold rush for data. If 3I, Atlas, formed around a different kind of star, its ice chemistry could be totally different from anything in our solar system. The ratio of deuterium to hydrogen in its water could tell us whether other planetary systems make oceans like ours or something completely alien. Keck Observatory's spectra can help reveal surface minerals. ESO's polarimetry can hint at whether the surface is fluffy dust, compact rock, or layered ice. Webb's infrared sensors can pick out organic molecules. If those molecules look different from what we've cataloged in local comets, it rewrites part of our story about how common certain building blocks of life might be across the galaxy. And there's another layer that makes scientists uneasy. The path of 3I, Atlas, through the inner solar system means it passes close enough to planets that spacecraft around Mars and Jupiter might catch side views Earth can't. NASA's MAVEN orbiter around Mars, ESA's Mars Express, and even Juno near Jupiter could, in theory, pick up brightness changes or dust activity from angles Earth-based telescopes miss. That means data will be fragmented across missions, agencies, and countries. Coordinating that data in real time is hard. Sharing it cleanly is even harder. Science moves slower than headlines. Meanwhile, the internet moves fast. The moment anyone hears NASA insider leak, imaginations go wild. People jump straight to secret crafts and hidden threats. That's not what's happening. What's happening is messier and more human. Raw data looks strange before it's cleaned. Early models look wrong before they're refined. Scientists argue, they disagree, they change their minds. That messy middle is where discovery lives. But it doesn't look good on social media. It looks like confusion. And confusion gets misread as cover-ups. There's also the planetary defense angle nobody likes to admit out loud. Even though 3I, Atlas, is not on a collision course with Earth, fast-moving interstellar objects are a nightmare scenario for future defense planning. Planetary defense teams train for asteroids that start in our own system, with years or decades of warning. Interstellar objects show up late, move fast, and leave quickly. The Vera Rubin Observatory is expected to find more of them once it's fully operational, which is great for science, but also means we'll be facing more late notice visitors. The more we learn from 3i, Atlas now, the better prepared we are for the next one, whether it's harmless or not. And here's where the challenge turns personal. We live in a time when we can watch another star system's leftovers pass through our cosmic backyard. That's insane when you think about it. Your ancestors could only guess what the stars were made of. Now we're measuring water ratios in ice that formed before our sun was born. The problem is, our tools are still limited by where we stand. The sun blinds us. Distances shrink details. And the clock never slows down. So astronomers are racing two enemies at once: distance and time. Every day that passes, 3i Atlas changes. Every hour, its angle shifts. Every week, it gets closer to the sun than farther away, carrying its secrets with it. If we miss the key moments, those secrets are gone for good. And that's why the mood around this object feels tense in labs and observatories. Not fear, urgency, the quiet kind. The kind where people stop speculating and start checking their code one more time. The kind where late-night emails fly between NASA, JPL, ESO, and Harvard Smithsonian teams. Not because something is wrong, but because nobody wants to miss the one detail that explains everything. One of the first things scientists do when something doesn't behave normally is try to break their own ideas. They actively look for boring explanations, because boring explanations are usually the right ones. So with 3i, Atlas, teams at NASA's Jet Propulsion Laboratory and the Harvard Smithsonian Center for Astrophysics started by asking a simple question: what natural processes could make a comet look this weird from far away? There are a few real possibilities. One is orientation. If a comet is spinning in a strange way, jets of dust can appear to point in odd directions depending on how sunlight hits it. Imagine a garden hose spinning in your hand. The spray pattern looks chaotic from one angle and smooth from another. Add distance, glare from the sun, and noisy data. And what looks impossible can sometimes be a trick of geometry. Another possibility is composition. Not all comets are made the same way. Some are rich in carbon monoxide and carbon dioxide ice, which can sublimate farther from the sun than water ice. That means they can start acting comet-like much earlier, at distances where we don't expect activity. ESO researchers have seen similar behavior in some long-period comets from our own Oort cloud. They don't break the rules, they just follow a different set of rules. Then there's dust size. If the dust grains coming off 3i, Atlas are unusually large or oddly shaped, sunlight pushes on them differently. That changes the shape and direction of the tail. Hubble spectrograph records from earlier comets show that grain size alone can flip how a tail looks from Earth, even when nothing exotic is happening. So far, none of that requires anything mysterious. It just requires us to accept that our sample size for interstellar objects is tiny. We've seen only a few. That's like trying to define what normal birds look like after seeing a pigeon, a penguin, and a peacock. The category exists. The variety is wild. But here's where it gets interesting. Even after throwing every normal explanation at the data, there are still things that don't sit comfortably. The speed of 3i, Atlas, is high. Not impossible, but high. Its brightness curve doesn't line up neatly with standard comet models. The lack of early gas detection is unusual, and its path through the inner solar system is statistically rare, even if not impossible. This is the part where careful scientists do something the internet often misreads. They don't jump to conclusions, they widen the box. Researchers working with data from the James Webb Space Telescope are now comparing 3i, Atlas, to comets from different parts of our own solar system. Objects from the Kuiper Belt behave differently from objects kicked in from the Oort cloud. Now imagine adding a third category: objects formed around other stars, under different radiation fields, with different dust chemistry, different ice mixtures, and different thermal histories. That's not sci-fi, that's just astrophysics. If 3i Atlas formed near a cooler red dwarf, its ices might be dominated by compounds we rarely see in our local comets. If it formed in a denser stellar nursery, Radiation could have baked its surface in a way that changes how it reacts to sunlight now. That could explain why it looks off without requiring anything exotic. This is where observatories like Keck in Hawaii and the European Southern Observatory matter so much. They can separate light into fingerprints of elements and molecules. They can tell us if we're seeing water ice, carbon monoxide, silicates, or something stranger but still natural. Webb adds infrared vision, which can pick up heat signatures that tell us how the surface is warming and cooling as the object spins. And then there's Vera Rubin Observatory, which will soon flood astronomy with data. Rubin isn't just about pretty pictures, it's about catching things early. The next interstellar object might be found months earlier than 3I Atlas was. That changes everything. Early discovery means more time to plan observations, more time to cross-check, more time to catch behavior before the sun hides it. Now, here's the uncomfortable truth scientists talk about behind closed doors. Even if 3I Atlas turns out to be just a comet, that's still huge. It means the galaxy is tossing ancient debris into our neighborhood, and those debris carry chemistry from other star systems. Some of that chemistry might look like early ingredients for life. Some might look totally foreign. Either way, it changes how we think about where life's building blocks come from. This ties back to work done at places like Stanford, where researchers have long discussed ideas like Ronald Bracewell's early concepts of how signals or probes might move through interstellar space. Not because anyone thinks 3I Atlas is a probe, but because interstellar travel and interstellar debris are real topics in astrophysics. The galaxy is not empty. It's full of moving stuff. Most of it is boring. A tiny fraction of it teaches us something new, and this is where the tension lives. We don't need secret plots for the story to be big. The big part is that 3I Atlas forces us to admit how little we've sampled the galaxy. We've studied our own solar system in detail. We've barely tasted what's out there. Every interstellar visitor is like a message in a bottle from a place we'll never reach in our lifetimes. The challenge is that the bottle is flying past at highway speeds, wrapped in sunlight and vanishing behind the sun when we most want to read the label. And here's the quiet fear scientists won't put in headlines. If we miss the key data now, we might not get another chance for decades. Interstellar objects don't line up on a schedule for our convenience. The next one could come tomorrow, or in 50 years, or in 500. We don't control the timing. We only control how well prepared we are when it happens. That's why teams across NASA, JPL, ESO, Keck, and the Harvard-Smithsonian Center for Astrophysics are treating this as a rehearsal for the future. Not for threats, for discovery. For the moment when the galaxy hands us something unexpected again. When 3I Atlas slips behind the sun, something subtle but important happens to the science. For a short window, we lose direct eyes on it. Hubble can't point too close to the sun without risk. James Webb has strict pointing limits to protect its instruments. Even ground observatories like Keck and ESO's Very Large Telescope have to back off because the glare overwhelms faint signals. So for a while, the object that caused all this debate becomes invisible. Not gone, just hidden. This blackout period isn't suspicious on its own. It happens to planets, comets, and spacecraft all the time. Voyager 1 telemetry data, for example, goes silent during solar conjunctions because the sun's interference drowns out the signal. That's normal space physics. But the timing still stings. Because the most violent changes in a comet's life often happen near the sunday. That's when ices crack, surfaces, shed layers, and internal pockets vent. If 3I Atlas is going to do anything dramatic, this is when it would happen. And we're blind right when the pressure peaks. Teams at NASA Jet Propulsion Laboratory have been running forward models of what might happen during that unseen passage. They feed in Webb's early infrared data, Hubble's light curves, and ESO spectra, then let the physics play out. Some models show a mild brightening and a slow fade. Others show the possibility of fragmentation. A few suggest a sudden outburst, where trapped gases break free all at once, briefly turning the object into a glowing beacon before it settles down again. But none of these outcomes are shocking. Comets do this all the time. What's different here is that if it breaks apart or changes shape while hidden, we only find out after the fact, we don't see the event. We only see the aftermath. Imagine watching smoke drift out of a room without seeing the fire. You know something happened inside. You just don't know what. This is where the story starts to split into two paths. If 3I, Atlas, comes back into view looking mostly the same, then a lot of the tension fades. The odd features can be chalked up to weird but natural chemistry from another star system. That would still be an incredible result. We'd be studying matter older than our sun, shaped by alien radiation fields, carrying the chemical memory of another planetary system. That's science gold. But if it comes back, changed, fragmented, or suddenly gassy after showing no gas before, then the debate flares up again. Because sudden shifts mean sudden internal changes. And sudden internal changes tell us about structure. At the Harvard-Smithsonian Center for Astrophysics, researchers have been comparing this to what happened with 2I, Borisov. Borisov looked calm at first, then broke apart near perihelion. That breakup taught us it was fragile, more like a loose pile of ices and dust than a solid rock. If 3I, Atlas behaves differently, it means interstellar objects don't all share the same internal build. Some may be fluffy, some may be tough, some may be layered like onions, with crusts baked hard by cosmic radiation. James Webb's infrared data is especially important here. Webb can see heat. After perihelion, the way heat moves across the surface will tell scientists whether 3I, Atlas, is covered in insulating dust, shiny ice, or darker material that absorbs sunlight. Each option points to a different history. There's also a quiet race happening with Mars missions. Spacecraft like MAVEN orbiting Mars and instruments on the surface can sometimes catch light from passing comets at angles Earth can't see. The geometry is tricky, but engineers at NASA, JPL, love tricky geometry. They've used odd alignments before to catch things we'd otherwise miss. Even a faint detection from Mars' side of the sun could fill in gaps in the story. And then there's the long view. Vera Rubin Observatory is about to change how often we catch these visitors early. Rubin's job is to scan the whole sky over and over, night after night. The next interstellar object might be spotted months earlier than 3I Atlas was. That means future stories won't hinge on a single blackout window. We'll have baselines. We'll see how these objects behave far from the sun when nothing dramatic is supposed to happen. That's how science really advances. Not with one mystery, but with patterns. Right now, 3I Atlas sits in the uncomfortable space between rare and normal. Rare because we've only seen a few. Normal because the galaxy is old, busy, and messy. Stuff flies between stars all the time. We just haven't been good at catching it until recently. The problem, the real one, isn't that 3I Atlas is strange. The problem is that our expectations are built on a tiny sample of space. We built rules for comets based on our backyard. Now something from across the galaxy shows up and refuses to follow our local habits. That doesn't mean it's wrong. It means our rulebook is incomplete. And the next few weeks after perihelion are where that rulebook either grows up a little or gets torn up and rewritten. Once 3I Atlas comes back out from behind the sun, the first thing astronomers will look for is not beauty shots. They'll look for damage. Did the brightness change more than expected? Did the shape of the coma spread wider or tighter? Did new jets appear that weren't there before? Those tiny details are how scientists read stress, the same way doctors read small changes in a heartbeat. Teams working with Hubble spectrograph records are already lining up pre- and post-perihelion data. So the moment the object reappears, they can compare what changed while it was hidden. James Webb Space Telescope will go after heat patterns. If a new hotspot appears, it means fresh material was exposed. Fresh material is gold for science because it hasn't been cooked by sunlight before. It's like cutting into a sealed loaf of bread and seeing the inside for the first time. At the European Southern Observatory, astronomers are planning rapid response observations the moment the glare eases. They've done this before with fragile comets that fell apart near the Sunday. The goal isn't just to take pictures, but to track how fast the dust cloud expands. The speed of that spread tells you how tightly the object was holding itself together. If the dust expands slowly, the body is dense. If it explodes outward fast, the body was fragile. This matters because density tells us how planets may form around other stars. Most of what we know about planet building comes from our own system. But 3I, Atlas, formed somewhere else under a different star with different gravity, different radiation, and a different disk of material. It is a free sample from another cosmic kitchen. Harvard Smithsonian researchers have called these objects natural sample return missions because nature did the hard work of bringing them here. There's also a quiet worry scientists won't say out loud in press releases, but you'll hear in hallways at places like JPL and Keck Observatory. What if 3I, Atlas, behaves in a way we've never seen before? Not weird in a spooky way, weird in a physics way. For example, if it shows no gas, even after perihelion, that would challenge how we classify comets at all. Gas is what makes a comet a comet. Without it, you're looking at something closer to a dry rock that somehow still throws dust. That would force a rethink of how objects survive long trips between stars. Another quiet question is whether interstellar objects are more baked than local comets. Traveling through deep space for billions of years means being hit by cosmic rays nonstop. Stanford researchers studying Bracewell-style interstellar probes once modeled how radiation changes materials over time. Those same models now help comet scientists ask whether 3I, Atlas, has a radiation-hardened crust, like a loaf of bread with a tough outer skin. If that crust cracks near the sun, it could suddenly release material that has never seen daylight in the history of our solar system. That's not sci-fi. That's just geology in space. And it matters because the chemistry of that released material could tell us how common water and organic molecules are around other stars. Arecibo legacy data helps scientists study how radio waves bounce off comet surfaces, giving hints about texture. Combine that with Webb's chemistry readings and Hubble's motion tracking, and suddenly this one object becomes a full lab. There's also a human side to this story that rarely makes headlines. People working on these observations are exhausted, real exhausted. Time on Hubble and Webb is fought over like front row seats at a championship game. Teams at NASA JPL coordinate with ESO, Keck, and universities across time zones. Someone is always awake, checking data, waiting for the next window to open. And yet, none of them know if the payoff will be huge or quietly normal. That's the risk of frontier science. You might spend months chasing a mystery that ends with, it's just a strange comet. But even that result matters. It tells us the galaxy is more diverse than our backyard. The bigger picture is this. Interstellar objects are no longer one-off legends. With Vera Rubin Observatory online, we are about to see many more. 3I, Atlas, is not the end of a story. It's the first chapter of a new era. An era where our solar system isn't just a closed neighborhood, but a busy street where strangers pass through. Some will be boring. Some will be weird. Some will force us to rewrite parts of physics textbooks. And the only way we'll know which is by paying attention when the next visitor shows up. As the weeks pass and 3I, Atlas, keeps moving, the story slowly shifts from raw surprise to long-term impact. And this is the part most people miss. The real discovery isn't just what this object is, but what it teaches us about how often these visitors pass through our cosmic neighborhood without anyone noticing. Before the Vera Rubin Observatory started wide-field scanning, astronomers believed interstellar objects were rare, maybe once every few decades. But early simulations from teams working with the Rubin data pipeline suggest we may have been undercounting them by a huge margin. Many are small, faint, and fast. They slip through like shadows between the stars. 3I, Atlas, is loud and bright, which is why we caught it. But for every loud visitor, there may be thousands of quiet ones we never see. This changes how we think about space itself. The space between stars isn't empty. It's more like a slow river of debris from broken planets, shattered moons, and ancient systems that died long before our sun was born. Harvard Smithsonian astronomers have pointed out that our solar system is constantly swimming through this galactic driftwood. We just haven't had the tools to notice most of it until now. The moment Rubin reaches full survey mode, this river becomes visible. And when that happens, 3I, Atlas, won't feel like a freak event anymore. It will feel like the first clear face we recognize in a crowd we didn't know was there. There's another layer to this that matters for Earth, and it's not fear-based. It's practical. Planetary defense teams at NASA JPL use near-Earth objects to test how well we can spot and track fast movers. Interstellar objects are the hardest case. They move faster than typical asteroids, come from random directions, and don't give us much warning time. 3I, Atlas, is basically a stress test for the entire detection system. The good news is this: we saw it early, we tracked it, we predicted where it will be. That means the early warning network works. Not perfectly, but well enough to give scientists time to study and, if needed in the future, plan responses. This is the same mindset used when tracking potentially hazardous asteroids with the help of the Catalina Sky Survey and follow-ups from Keck Observatory. Every strange visitor is also a drill run for something that might actually matter for safety one day. Then there's the quiet philosophical shift happening inside astronomy departments. People who study comets used to think of them as local fossils, dirty snowballs left over from when the planets formed. 3I, Atlas is not local. It's a foreign fossil. It formed around another star. That means its ice, dust, and rock carry the history of a completely different system. If its water chemistry doesn't match Earth's oceans, that supports what teams at the Harvard-Smithsonian Center for Astrophysics have long suspected, that there are many different recipes for water in the galaxy. Some stars make water that looks like ours, others don't. That matters for how common Earth-like planets might be. And here's a small detail that hits hard when you sit with it. This object is older than the Sunday. It formed when our solar system didn't exist yet. It drifted through the galaxy while planets were still forming here. It passed by stars that are now dead. Now, for a brief moment, it's passing us. That's not a threat. That's a reminder of scale. We tend to think of our sky as stable. Planets move in neat lines, stars seem fixed, but the galaxy is messy. Things wander, systems break. Debris travels for billions of years and sometimes brushes past young worlds like ours. The calm part of this story is that nothing about 3I Atlas is dangerous. It's not on a collision path. It's not slowing down. It's not changing direction toward Earth. It's doing what interstellar debris does, passing through, following gravity, then heading back into the dark between stars. But the deep part of the story is that humanity has reached a point where we can finally notice these visitors. For most of history, they came and went unseen. Now, with Webb, Hubble, Rubin, and networks coordinated by JPL and ESO, we are finally paying attention to the traffic between stars. That's a quiet milestone for our species. There's another shift happening that doesn't get talked about much, and it's not about telescopes or data. It's about how scientists feel when something new breaks the pattern they're used to seeing. For decades, comet science was comfortable. Not boring, but predictable. You see ice heat up, gas comes out, dust follows the solar wind, tails point away from the sun, and brightness rises and falls in patterns you can model. Then objects like 3I, Atlas, show up and politely ignore the rulebook. That doesn't mean anything spooky is going on. It means the rulebook was incomplete. This is how science actually moves forward. Not with fireworks, but with discomfort. A few researchers at the European Southern Observatory describe this moment as model stress, which is a fancy way of saying the math we trusted needs updates. The dust tail pointing sunward, the weak gas signature, the odd light curve, all of that forces new simulations, new lab tests, new ways to think about how interstellar ice behaves when it meets a star that isn't the one it formed around. The James Webb Space Telescope is a big deal here because it doesn't just take pretty pictures. It reads heat and chemistry. Webb can spot carbon compounds, water vapor, and exotic ices that Hubble can't easily separate. Teams working with Webb and the Harvard-Smithsonian Center for Astrophysics are trying to answer a simple question that sounds small but isn't. Is this object more like our comets or more like something we've never sampled before? If the chemistry is familiar, it means planet building across the galaxy may follow similar rules. If it's strange, that means there are whole families of planet systems built with materials we don't even see here. And then there's the human side of the story. which is easy to miss if you only focus on numbers. A lot of young astronomers are getting their first big discovery moment from 3i, Atlas. Students who started grad school thinking they'd spend years cataloging tiny dots in data suddenly have a front row seat to a visitor from another star system. For them, this isn't just a comet, it's the reason they chose this career. Some of the earliest alerts came from automated systems at the Vera Rubin Observatory during testing runs. That's poetic in a nerdy way. The newest eye in the sky spotted something ancient. Old traveler meets new watcher. That's how progress looks most days. There's also a lesson here for the public. When headlines scream about mysterious objects or NASA leaks, it's easy to think scientists are hiding things. The truth is usually more boring and more honest. Data comes in messy. It takes time to check it. Early images can be misleading. Teams at NASA, JPL, ESO, and the Space Telescope Science Institute don't rush because rushing gets things wrong. That doesn't make for dramatic stories, but it's how you build real understanding. When you hear that a feature was unexpected, that doesn't mean someone panicked. It means the universe just reminded us that it doesn't owe us simple answers. And here's the part that quietly changes how we think about home. If objects like 3i, Atlas, pass through star systems all the time, then our solar system is not a sealed bubble. It's part of a bigger flow. Material from other systems has likely passed through here before. Tiny grains from distant stars may already be in our oceans, our soil, even in the dust on your window right now. We are not just looking out into space. We are sitting inside it. That sounds obvious, but it lands differently when you realize the space between stars is not empty, it's shared. There's one more layer to this story that usually stays buried in research papers. And it matters because it changes what interstellar visitor really means. When scientists at NASA's Jet Propulsion Laboratory model how objects like 3i, Atlas, get kicked out of their home systems, the math points to violent childhoods. Young star systems are chaotic. Giant planets migrate, gravity slingshots, debris outward, and whole swarms of icy bodies get flung into the dark. Most of them wander the galaxy forever, never touching another star again. A tiny fraction pass close enough to be captured or briefly lit up. And that's what we're seeing now. So this object is not just old, it's a survivor. It lived through the early mess of another star system, drifted for millions or billions of years, then crossed the path of our sun for a brief hello. That alone is wild, and it reframes the story from what is this thing doing here to how many like this have passed unnoticed. This is where the Vera Rubin Observatory becomes huge for the future. Rubin is designed to scan the whole sky over and over, catching fast-moving, faint objects that older surveys missed. Astronomers at Stanford and Caltech expect Rubin to find dozens of interstellar visitors every year once it's fully operational. Think about that. What feels rare right now might turn out to be common. We just didn't have the eyes to see it before. If that happens, the tone of these discoveries will change. Instead of panic headlines, you'll see patterns. Families of objects with similar speeds, groups with similar chemistry, maybe even clusters that hint at shared origins, the way meteorites on Earth can sometimes be traced back to the same parent body. Keck Observatory in Hawaii is already lining up follow-up observations to get high-resolution spectra as soon as viewing angles allow. That's how you move from weird behavior to we understand the physics behind this. Each wavelength tells a different part of the story. Infrared for heat and ices, optical for dust and shape, ultraviolet for how the solar wind is slamming into it. And here's a quiet truth a lot of space fans don't hear often enough. Even when something looks strange, nature usually has an explanation that feels boring in hindsight. The Pioneer anomaly turned out to be heat leaking from spacecraft. Fast radio bursts were once called impossible until we found magnetars could make them. The universe doesn't need secret agendas to surprise us. It's already complicated enough. But that doesn't make this less meaningful. It makes it better. Because every time we spot an object from another star system, we're not just seeing a rock, we're sampling another planet factory, another recipe for worlds, another version of how dust turns into planets, moons, maybe oceans, maybe life. And that brings the story back to us. Our solar system didn't form in isolation. The sun was born in a cluster with other stars. Early on, our system likely traded material with its neighbors. Tiny bits of other worlds may be locked inside comets in our own Oort cloud right now. The line between here and out there has always been thinner than we thought. So when 3I, Atlas, fades back into the dark and disappears from our telescopes, it won't be a goodbye. It'll be proof of traffic. Proof that the galaxy is not empty space between islands, but a river with debris flowing through it, carrying stories from places we haven't seen yet. Here's the part that quietly changes how you look at the sky at night. For decades, astronomers treated interstellar space like an empty highway. Vast, dark, mostly silent. A few rare travelers pass through, and that's it. But the data from objects like 3I, Atlas, is forcing a rethink. Space isn't empty, it's busy. It's just busy with things too small, too faint, and too fast for our older tools to catch. When the Harvard-Smithsonian Center for Astrophysics runs population models of rogue objects, the numbers get uncomfortable. For every interstellar visitor we notice, there could be millions drifting unseen through our neighborhood at any moment. Most are pebble-sized, some are car-sized, a few are mountain-sized. They're relics from planet formation all across the Milky Way, kicked out like cosmic shrapnel. Now think about what that means for impact risk, not panic perspective. NASA's Planetary Defense Coordination Office tracks near-Earth objects that come from our own solar system. Those are the ones that pose real, measurable risk. Interstellar visitors like 3I, Atlas, move too fast and on paths that make close Earth encounters extremely rare. The danger isn't that one is aiming at us. The danger is that we've been undercounting how busy the cosmic shooting gallery really is. This is why the James Webb Space Telescope is being used in ways people don't usually talk about on social media. Webb isn't just looking at galaxies and exoplanets. Its infrared instruments can read the heat signatures and chemical fingerprints of fast-moving bodies. That's how teams at NASA, JPL, and the European Southern Observatory hope to tell whether 3I, Atlas, is rich in carbon compounds, water, ice, or more exotic ices like carbon monoxide and carbon dioxide that freeze only in deep cold. If Webb sees a mix that doesn't match anything from our solar system, that's huge. It's like tasting food from a kitchen you've never visited. You learn what ingredients exist elsewhere in the galaxy. That feeds directly into planet science. What kinds of planets form around other stars? What kinds of atmospheres do they end up with? What building blocks for life are common? There's also a human angle here that gets overlooked. When Voyager 1 crossed into interstellar space, it became our first probe to feel the weather of the galaxy outside the sun's bubble. Its telemetry showed changes in particle density and magnetic fields. Now imagine combining that kind of in situ data with samples we can only observe from afar, like 3I, Atlas. Together they start to paint a real map of our neighborhood beyond the heliosphere. And here's the quiet part, nobody headlines. The more we understand these visitors, the less scary they become. Mystery feels threatening when you don't know the rules. Once you do, it turns into context. A strange comet stops being a threat and starts being a messenger from another system's history. Now let's zoom out a bit, because the story of 3I, Atlas, isn't just about one object. It's about how fast our eyes on the sky are leveling up. For most of human history, space was a slow story. You'd wait years, sometimes decades, between big discoveries. That changed the moment wide field surveys came online. The Vera C. Rubin Observatory in Chile is built for exactly this kind of moment. Its job is to scan the whole visible sky over and over, night after night, catching anything that moves, flickers, or wasn't there before. That's how 3I Atlas was picked up so early in its inbound run. Not by luck, by design. Rubin's data doesn't just find objects, it builds timelines. Astronomers can rewind the tape and spot faint precovery images of objects before anyone knew to look for them. That's how teams piece together the path of a visitor, its speed, and how long it's been in our neighborhood. When those tracks are cross-checked with archives from Hubble's spectrograph records and ground-based observatories like Keck in Hawaii, the picture sharpens fast. This is where the calm work happens. No drama, just pattern matching. Scientists at NASA JPL take the orbit fits and run thousands of simulations. They ask boring questions with big payoffs. How stable is this path? Does the object show tiny changes in speed that could come from outgassing? Does sunlight alone explain what we're seeing? Or is there an extra push? When Oumuamua sped up without a visible gas tail, it forced a rethink. With 3I, Atlas, the goal is to not get surprised again. There's also a race against time built into every interstellar visitor. These objects move fast. By the time you confirm what you're looking at, the window to study it is already closing. That's why observatories coordinate. The European Southern Observatory handles deep optical imaging. NASA schedules infrared time on Webb. Radio astronomers lean on legacy Arecibo datasets to compare scattering patterns from past objects. Different tools, same target, same narrow window. And this is where the science gets quietly emotional. You're staring at something that formed around another star billions of years ago, and you have weeks to learn what you can before it's gone forever. No sample return, no second chance. Just photons hitting your sensors one last time. This is also why speculation flares up online. Gaps in data invite stories. When agencies say, "We don't know yet," people hear they're hiding something. In reality, the timeline of science is slow compared to the speed of rumor. It takes weeks to calibrate instruments, months to publish solid results, and years to agree on what it all means. So the next stretch of the story is simple and tense in a quiet way. More nights of tracking, more spectra, more careful checks. Not because anyone expects a threat, but because this is rare. Interstellar visitors don't wait for us to get ready. They pass through whether we're watching or not. Here's the part most people don't realize. Even when we spot something early, we're still mostly blind to what's happening on and inside these visitors. Telescopes see light, heat, and motion. They don't see structure the way a close-up probe would. So scientists lean on clues that feel indirect, almost like reading footprints in sand. One of the biggest clues is how the object reacts to sunlight. As 3I, Atlas, gets closer to the sun, its surface heats up. If it's a normal comet, ice is turned to gas jets push dust, and the tail grows and points away from the sunday. That's the basic physics. Teams at the Harvard-Smithsonian Center for Astrophysics and NASA JPL model this process in detail. They compare the brightness curve to lab tests of ice and dust under heat. When the curve doesn't match expectations, it doesn't mean alien tech. It means the mix of ices might be different, or the surface could be coated in a dark, crusty layer that traps gas until it vents and bursts. James Webb adds another layer because infrared light is basically heat vision for space. Webb doesn't just tell us that something is warm, it tells us what kind of molecules are there by the way they glow. Carbon dioxide leaves one fingerprint. Carbon monoxide leaves another. Water ice has its own signature. When Webb sees those patterns, researchers can say, okay, this looks like a comet, but not one from around here. That alone is huge. It means we're sampling chemistry from another star system without leaving Earth. There's also the question of shape and spin. When light curves rise and fall in a steady rhythm, it usually means the object is tumbling. A long, thin body flashes light differently than a round one. Teams working with Keck Observatory data and Hubble spectrograph records try to match these patterns to models. It's like guessing the shape of a spinning key by watching how light glints off it. You're not seeing the key, just the flashes. And then there's dust. Dust is messy, but it tells stories. The size of dust grains changes how the tail looks. Fine dust makes a smooth glow. Bigger chunks scatter light differently. If the dust tail points in odd directions, that can mean jets are coming from one side more than the other, or that the object is rotating in a weird way. These are the kinds of details researchers argue over in long Zoom calls that never make headlines. This slow work matters because it sets boundaries. It tells us what's normal, what's rare, and what's still unexplained. Most mysteries in space don't end with a big reveal. They end with better models, better limits, fewer wrong ideas. So as 3I, Atlas, keeps moving, What's really happening behind the scenes is a quiet pileup of data. Every night adds a few more pieces to the puzzle. And when the object finally fades into the dark again, those pieces are all we'll ever have. Another layer to this story is how fast the global response has grown. 10 years ago, an interstellar visitor could slip through with only a few telescopes paying attention. Today, the moment something odd shows up, alerts bounce around the world in minutes. Observatories in Chile, Hawaii, South Africa, and the Canary Islands line up their schedules. The Vera C. Rubin Observatory's survey pipeline is built for this exact job, scanning huge chunks of sky and flagging anything that doesn't belong. When something like 3I Atlas appears, it's like a stadium light turning on. Everyone sees it at once. This matters because timing is everything. These objects move fast. Miss a week, and you lose a big part of the story. NASA's Jet Propulsion Laboratory coordinates follow-ups, passing refined orbit data to teams running Hubble, Webb, and ground telescopes like Keck. The European Southern Observatory loops in its own networks. Even old Arecibo legacy data comes into play when scientists look for past flybys that might match similar paths. It's detective work on a global scale, and the clock is always ticking. There's also a quiet race happening in mission planning rooms. People at JPL and partner universities sketch ideas for interceptor missions. Tiny spacecraft that could launch fast, hitch a gravity assist, and take a close look at the next visitor. The technology is hard, the timelines are brutal, and budgets are tight. But the idea keeps coming back because this is the only way to stop guessing. If we could fly past one of these objects even once, we'd learn more in hours than we do from years of distant watching. All of this sits on top of a bigger question that scientists don't love to say out loud, but they think about it anyway. How common are these visitors? If we've seen 3 in less than a decade, what does that say about the space between stars? Teams at the Harvard-Smithsonian Center for Astrophysics in Stanford have been modeling the density of interstellar debris in the Milky Way. The numbers hint that our solar system might be swimming in these things. Most are small, dark, and invisible to us. We only notice the rare bright ones that wander too close to the sunday. That flips the story on its head. Instead of a strange thing just arrived, it becomes we've been getting flybys forever and only recently learned how to notice. It's like living next to a highway your whole life and only now realizing cars have been passing in the dark. As 3I Atlas fades from view, the focus shifts forward. What will the next one look like? Will it behave more like a normal comet or throw us another curveball? Every new detection sharpens our tools, our models, and our expectations. The mystery isn't just about this one object. It's about what kind of neighborhood we actually live in out here between the stars. There's another piece most people don't hear about, and it's how messy the data really is in the early days. When an object first shows up, the orbit is rough. Tiny errors in the first few measurements can swing predictions by millions of kilometers. Teams at NASA's Jet Propulsion Laboratory and the Minor Planet Center work around the clock refining those numbers as new observations roll in. Each fresh data point tightens the curve, like pulling a loose thread until the shape finally holds. This is why you'll see headlines change. One day it's close pass, the next day it's farther than expected. It's not flip-flopping. It's science doing its slow, careful work. Hubble's spectrograph adds detail about what the object is made of. Webb's infrared eyes pick up heat patterns that hint at whether there's ice, dust, or something stranger. The Keck Observatory in Hawaii fills in gaps when clouds block other sights. Every telescope brings a different puzzle piece, and none of them tell the full story alone. There's also a human side to this. Astronomers don't just stare at screens. They argue, they doubt their own results, they rerun models at 3 in the morning because something doesn't sit right. People at ESO and the Vera Rubin Observatory have talked about the strange feeling of knowing you're watching something that formed around another star. It's like holding a postcard from a place you can never visit. The data might look cold and technical, but the emotion behind it is real. And then there's the public side. The moment a story like this breaks, it explodes online. Some takes are thoughtful, some go straight to wild claims. That noise can drown out the careful voices of scientists trying to explain what we know and what we don't. Groups at universities like Harvard and Stanford end up spending just as much time correcting bad info as they do analyzing spectra. It's frustrating, but it's part of the job now. Space news doesn't live in journals anymore. It lives on feeds, timelines, and late-night clips. All of this pressure makes one thing clear. We're still early in learning how to read these visitors. We're building the rulebook as we go. Each strange detail from 3I, Atlas, isn't just about this one object. It's a test of how ready we are to deal with the unknown when it drifts into our backyard from deep space. There's also the quiet questions scientists don't say out loud at press briefings, but wrestle with in private meetings. What if some of what we're seeing doesn't fit our boxes, because our boxes are too small? Astronomy is built on patterns. Comets behave this way. Asteroids behave that way. Interstellar visitors should be rare and messy and hard to track. Then something like 3I, Atlas, shows up and starts bending those neat lines. Not breaking physics, but stretching our comfort zone. At the Harvard-Smithsonian Center for Astrophysics, researchers have been comparing 3I, Atlas, with everything we've learned from Oumuamua and Borisov. Oumuamua had that odd push that didn't match simple gas jets. Borisov looked more normal, then surprised everyone by breaking apart near the Sunday. Each one forced a rewrite of what normal even means for objects that didn't grow up in our solar system. Now this one adds new wrinkles. The sunward dust tail, the tight planetary flybys, the timing around solar glare. None of those alone are shocking. Together they make you pause. The tools we use to study these objects are also hitting their limits. Arecibo's legacy radar data still helps model how radio waves bounce off small bodies, but we don't have a working dish like that anymore. We lean more on optical and infrared eyes now. Webb gives us heat and chemistry. Hubble gives us fine detail in visible light. Ground-based networks fill in the rest. Even Voyager 1's old telemetry helps in a strange way, reminding scientists how space, hardware ages, and how data can drift over time. Every reference point matters when you're trying to tell if a weird signal is real or just noise. And here's the uncomfortable truth. We can't chase this thing. It's moving too fast. By the time anyone could design, build, and launch a probe, 3I, Atlas would already be gone, slipping back into the dark between stars. That means this is all remote forensics, light curves, spectra, motion against distant stars. It's like trying to solve a crime by watching a blurry security camera clip of the suspect running away. You get clues, but never the full picture. So the stakes feel higher than they actually are in terms of danger, but lower in terms of control. There's no button to push, no mission to launch in time. Just watching, measuring, and learning what we can before the door closes. That's the strange tension in moments like this. You're staring at a once-in-a-lifetime visitor, and all you can really do is pay attention. The tension peaks when the final wave of high-resolution data lands on the desks of teams at NASA's Jet Propulsion Laboratory, the European Southern Observatory, and the Harvard-Smithsonian Center for Astrophysics almost at the same time. Hubble's spectrograph confirms the dust tail really is behaving in a way no textbook comet should. James Webb's infrared view fills in the missing heat profile, showing patches that warm and cool faster than simple ice can explain. Arecibo's old radar models are pulled from archives to compare echoes from past comets. And 3I, Atlas, still doesn't match the pattern. Even Voyager 1's distant plasma data is checked for background changes as this visitor slices through the solar wind. The room goes quiet for a moment, not because anyone thinks the sky is about to fall, but because the numbers finally agree on one thing. This object is genuinely different. Not magical, not a movie monster, just different enough to break our comfort zone. That's the real shock. After weeks of arguments, the science settles into a strange calm. The models tighten, the error bars shrink. The mystery doesn't vanish, but it becomes sharper, more honest. What we're seeing is an interstellar body shaped by a star system that is not ours, moving through our neighborhood like a tourist who doesn't speak our language. It doesn't need to be anything more than that to be incredible. When the glare of the sun finally releases its grip and 3i Atlas comes back into view, the story won't end. It will simply become clearer. New spectra will tell us what ices survive the heat. New images from Keck Observatory and the Very Large Telescope will sketch its shape. Webb will likely pick out chemicals no comet from our own backyard has ever shown us. And years from now, when the Vera Rubin Observatory catalogs the next visitor from deep space, we'll realize this wasn't a one-off event. It was the moment we learned how to watch properly. The universe didn't suddenly become more dramatic. We just got better at noticing its quiet surprises. If you want to stay with this story, as the next data drops and the picture sharpens, subscribe and keep the next video playing on your screen. Because what we're learning about 3i Atlas is teaching us how to read every stranger that crosses our sky after it. The tension peaks when the final wave of high-resolution data lands on the desks of teams at NASA's Jet Propulsion Laboratory, the European Southern Observatory, and the Harvard-Smithsonian Center for Astrophysics, almost at the same time. Hubble's spectrograph confirms the dust tail really is behaving in a way no textbook comet should. James Webb's infrared view fills in the missing heat profile, showing patches that warm and cool faster than simple ice can explain. Arecibo's old radar models are pulled from archives to compare echoes from past comets, and 3i Atlas still doesn't match the pattern. Even Voyager 1's distant plasma data is checked for background changes as this visitor slices through the solar wind. The room goes quiet for a moment, not because anyone thinks the sky is about to fall, but because the numbers finally agree on one thing. This object is genuinely different, not magical, not a movie monster, just different enough to break our comfort zone. That's the real shock. After weeks of arguments, the science settles into a strange calm. The models tighten, the error bars shrink. The mystery doesn't vanish, but it becomes sharper, more honest. What we're seeing is an interstellar body shaped by a star system that is not ours, moving through our neighborhood like a tourist who doesn't speak our language. It doesn't need to be anything more than that to be incredible. When the glare of the sun finally releases its grip and 3i Atlas comes back into view, the story won't end. It will simply become clearer. New spectra will tell us what ices survive the heat. New images from Keck Observatory and the Very Large Telescope will sketch its shape. Webb will likely pick out chemicals no comet from our own backyard has ever shown us. And years from now, when the Vera Rubin Observatory catalogs the next visitor from deep space, we'll realize this wasn't a one-off event. It was the moment we learned how to watch properly. The universe didn't suddenly become more dramatic. We just got better at noticing its quiet surprises. If you want to stay with this story as the next data drops and the picture sharpens, subscribe and keep the next video playing on your screen. Because what we're learning about 3i, Atlas is teaching us how to read every stranger that crosses our sky after it.